In this video, we will learn about evaluation metrics for a classifier. While training a model, we should somehow estimate how good its quality is. By knowing how well it is doing, we can compare it with other models and define the improvement path or choose the best option for some solution. For these purposes, a set of evaluation metrics were invented. Commonly used ones are confusion matrix, accuracy, precision, recall or sensitivity, F1 score, and area under the curve for an ROC curve. For simplicity of the discussion, we first look into the class when our class has just two classes. We are looking at mammograms, and our goal is to identify if this mammogram shows breast cancer or not. Since we are looking for breast cancer, the mammograms with breast cancer belong to the positive class, which is pretty ironic. The mammograms with no breast cancer belong to the negative class. The first way of showing accuracy is the confusion matrix. The confusion matrix is a table used to describe the accuracy of a classification model. The rows of the matrix represent predicted classes and the columns represent the ground truth. In some confusion matrices, rows and columns are switched, so be sure to read the labels when analyzing a confusion matrix. The name stems from the fact that it makes it easy to see if the system is confusing between two classes or mislabeling one class as another. The confusion matrix itself is not a performance measure, but the values inside it are the basis for a major part of performance metrics we'll discuss further. Let's look into the numbers that comprise the matrix. You will see there are four metrics: true positive, true negative, false positive, and false negative. The true false part of the name indicates whether the algorithm was right or wrong. So let's look at true positives. True positives are cases when the algorithm is right and the class is positive. In our case, it means that the mammogram shows breast cancer and the algorithm identified it. The next metric is true negatives. True negatives are cases when the algorithm is right and the class is negative. So the algorithm correctly identified a negative class. In our case, it means that the mammogram does not show breast cancer and the algorithm says that there is no breast cancer. So it's all good. Next is false positive. False positives are cases when the algorithm says breast cancer was detected, but in reality, there was no breast cancer. So it is a false positive. It is not a true positive. False negatives are when there was breast cancer, but the algorithm falsely said that it is negative, which means that there was no breast cancer. Next, look at the metric called accuracy. Formally, it is defined as the ratio of correct predictions to total predictions. So it is the fraction of predictions our model got right. In terms of true positives, true negatives, and false positives and false negatives, it is basically the ratio true positive plus true negative divided by the total number of samples, which is essentially true positive plus true negative plus false positive plus false negatives. The main drawback of accuracy as a metric is that it does not perform very well with imbalanced data set. Let's say in our mammogram example, there are only 5 positive cases of breast cancer and 95 cases do not have breast cancer. If our method classifies all samples as negative, which means that it predicts all samples do not have breast cancer, the values in the confusion matrix will be true positive is 0 because it's saying that all of them are negative. False positives is also 0. True negatives is 95 and false negatives is 5. So it will misclassify some of the negatives. However, if you look at the accuracy number, the accuracy is 95%, 95% of the time it is classifying things correctly because the data is imbalanced. 95% of the time there is no breast cancer, and therefore, even though this is a completely useless model that does not detect breast cancer, the accuracy is 95%, which is ridiculous. So we have to be very careful when we use metrics like this. We have to make sure that we are not talking about imbalanced data set. And when somebody reports numbers about accuracy, we should be careful what they are talking about. Nevertheless, accuracy is a very intuitive metric and is used very commonly, especially if the dataset is pretty much balanced. Next, look at a metric called precision, which is also called positive predictive value. It is the fraction of relevant instances among all retrieved instances. It gives us information about a classifier's performance with respect to false positive. Mathematically, it is given by true positive divided by true positive plus false positive. And as the name suggests, precision is all about being precise. In our example, it answers the question, if the result is positive, how sure can we be that the mammogram contains a breast cancer image? And when do we use it? If our main objective is to minimize false positives, then we need to make precision as close to 100% as possible. This is often the case in automotive or surveillance scenario. When the system helps the user identify situations like a pedestrian on the road or theft in the supermarket, and the triggers result in some extreme action, then we want the false positive to be really small or the precision to be very, very high, because there is a very heavy cost you pay for a false positive. Next, let's look at recall or sensitivity. Recall is the fraction of the total amount of true positives that were retrieved. It is also called the true positive rate. And in our example, let's say there were n cases of true positives in our dataset. Recall describes how many true positives out of the total n the model was able to find. So if we simply classify everything as positive, we will have 100% recall, since we will capture all of the cases of positive classes. Obviously, in this case, we'll have a very low precision. So recall and precision are used together. If we want to focus on minimizing the false negatives, we would want our recall to be as close to 100% as possible, without precision being too bad. For example, in medical diagnosis, it is crucial to exclude as many false negatives as possible. If a particular test is designed to detect a disease returns a negative result for a patient who does have it, that can have serious consequences and even lead to death. Precision and recall are typically used together so that we can assess the quality of the system. And usually there is a trade-off. When we try to increase the precision, the recall tends to go down. And when we try to increase the recall, the precision tends to go down. We want both of them to be very good. Now, let's look at another metric called the F1 score. As we saw, typically we need to estimate and assess both precision and recall. F1 score is a combination of the two metrics. It reaches its best value at 1, which is perfect precision and perfect recall, and worst at 0. In terms of applications, F1 score is preferable when you have a small positive class. There is a criticism of widespread use of the F1 score, though, since it gives equal importance to precision and recall. In practice, different types of misclassification incur different costs depending on the application. As we saw, in surveillance, precision matters more, and in medical analysis, recall is more important. Another curve which is very commonly used to judge the performance of a classifier is called the Receiver Operating Characteristic Curve, or the ROC curve. It is a graphical plot showing the performance of a classifier as its discrimination threshold is varied. Classification models typically analyze the data and output some value of confidence that it's an object of some class. So our model will look at the data and predict, say, with 60% confidence that there is breast cancer in the mammogram. We need to set a threshold on this value so that we can set a 0 or 1 value to the final output. Everything above it will be considered positive, and everything below the threshold will be considered negative. Depending on the algorithm and the task, we can select different values of this threshold. The ROC curve helps select the right threshold for our requirement on the true positive and false positive rate. The true positive rate, as we have already mentioned, is also called sensitivity or recall. The false positive rate is also known as the fallout or probability of false alarm. Out of all the samples that were not diagnosed as breast cancer, how many did the model incorrectly classify as breast cancer? Now, to plot the ROC curve, we need to measure a pair of true positive and false positive rates for different confidence threshold values. We then will put a confidence point on the plot for every such pair. Now we can analyze the curve we got by connecting these points to find the optimal confidence threshold. Lowering the threshold makes the model classify more items as positive, thus increasing the number of true positives at the cost of more false positives. Otherwise, increasing the threshold will lower the number of false positives, but there will be less likely true positives too. In a perfect case, there's a threshold that allows the model to split the classes perfectly. The true positive rate will be equal to 1, while the false positive rate will be 0. The resulting ROC curve will be a straight line glued to the upper left corner of the plot. So in practice, we want the ROC curve to be as close to the corner of the plot as possible. AUC stands for area under the ROC curve. It measures the entire two-dimensional area under the ROC curve, somewhere in the square from 0, 0 to 1, 1. The better the classification algorithm is, the higher the area under the ROC curve. The score ranges typically from 0.5 to 1, and the score being 1 is the ideal case where the true positive rate is 1 and the false positive rate is 0, which means we correctly classified all positive and negative samples in the dataset. The area under the curve is an aggregate performance measure across all possible classification thresholds. The area under the curve does have some drawbacks. First of all, AUC treats recall and true negative rate as equally important overall when averaged across all thresholds. That is not always what we want from a model. Depending on the application, we may be interested in a single point on the ROC curve and how the performance looks at that single point on the ROC curve. Next, we will cover the metrics that are used when the classifier has more than 2 classes. In this case, we do not have negatives. All the instances now have their own class. Even though binary classification can be a useful real-life task, multi-class classification is way more common. As an example, it is commonly used in various competitions and benchmarks. Let's look at the most popular multi-class classification competition out there. It is called ILS-VRC, which stands for ImageNet Large Scale Visual Recognition Challenge. We already know a little bit about the ImageNet competition. It is a very popular challenge for image classification with 1,000 different classes and over 1.2 million training images. There are 2 classification metrics that the challenge uses. One of them is called the top 1 error, and the next one is called top 5 error. In the case of top 1 score, you check if the top class, the one having the highest probability, is the same as the ground truth label. So it essentially is the accuracy metric we defined earlier. In the case of top 5 score, you check if the target label is one of the top 5 predictions. These top 5 predictions are nothing but the 5 classes with the highest probabilities. If that is true, then the prediction is considered a correct one. In both cases, the total score is the ratio of the correct predictions divided by all the predictions made by the model. Another way of looking at the performance is the confusion matrix. In case we have more than 2 classes, we can still build a confusion matrix. It will have n by n cells, where n is the number of classes. Let's look at an extended example where we have 4 classes: cats, dogs, apples, and cars. Recall that the rows represent the predicted output and the columns represent the ground truth. Now let's analyze what does our model predict when it looks at a dog. First, let's take a look at the table on the top. It uses absolute numbers of correct and incorrect predictions. Let's look at the dog column to see how well our model does to recognize them. We have 200 dog examples in the dataset in total. Our model correctly classifies a dog as a dog in 168 cases. In 24 cases, though, it mistakenly says it's a cat. In 6, it thinks it's a car. And in 2, it thinks it's an apple. Our data set here is not normalized. We have 500 cats, 200 dogs, 150 apples, and only 50 cars, which is 10 times less than the number of cats. This makes the absolute values of correct and wrong predictions not that convenient to look at. So people usually switch to normalized version of this table using the one below. On it, we can clearly see the strong and weak points of the model. In a perfect normalized confusion matrix, the diagonal elements should be 100% and all others should be 0. Analyzing the deviation from that provides an important insight into the nature of the errors in our model. For example, our model quite often confuses dogs with cats, and we need to think how we fix it by applying modification to the dataset or the algorithm. Because of that, the normalized confusion matrix are commonly used in many classification tasks. In the multi-class case, we can also compute the classification accuracy. To do that, we just need to compute the number of correct predictions versus total predictions. Now, you always have to keep in mind that when the data set is imbalanced, the accuracy does not always show the real performance. With this, we have covered most of the common metrics for classification. Of course, there are plenty of less common ways to measure the classification quality, for example, dice metric or specificity, but we won't cover those in this course. That's all for this video. Thank you.